So this video is the video support for the Dynamical Systems and Chaos coursework 6G6Z3003. So I'm just going to go straight to the questions. Question number 1 is concerned with the tent map. So in the notes you need to go to chapter 3 and if you remember we looked at the tent map when mu was equal to 2. So you'll find these notes on page 21. So here was the tent map with mu is 2, and in the class we found fixed points of period 1 and fixed points of period 2 and fixed points of period 3 when mu was equal to 2. Okay, so this is the map T of x, and this is the graph of T of x, and here we have T of x, and here is the graph of T of x. Now of course for your coursework you need to work with mu is 9/5, but the arguments are similar to what's used in the notes. Note also that you have to use pencil and rule in order to plot the graphs on graphical paper. You cannot plot them with MATLAB or Python. You need to determine the fixed points of periods 1, 2 and 3 and the stability of fixed points of period 2 only. For question number 2, we've got a 3-dimensional discrete system. And in the notes, if you look at the Gaussian map, then you'll see that the Gaussian map is a 2-dimensional system, but we can easily extend this to a 3-dimensional system. So the first part of the question is you're asked to find the fixed points. So we just solve xn plus 1 equals xn equals x, yn plus 1 equals yn equals y, zn plus 1 equals zn equals z. So you get 3 simultaneous equations, and then you need to solve those simultaneous equations in a similar way to we solve them with the Henon map. When we're looking for stability of fixed points, instead of using this Jacobian, which is a 2-dimensional Jacobian, we need a 3-dimensional Jacobian, so you would have dp dx, dp dy, dp dz, dq dx, dq dy, dq dz, and dr dx, dr dy, dr dz. And note that the fixed points are only stable if the modulus of all of the eigenvalues is less than 1. For part 1, we need to plot a bifurcation diagram, and an example similar to this can be found in chapter 5. So in chapter 5, you'll remember we were looking at the simple fiber ring resonator, and program 5C plots a bifurcation diagram for the simple fiber ring resonator. So here's program 5C. In this case, we ramp A up and A down. So this is the n times p max over n1. In your case, you will be ramping this weight, W21, you will be ramping it up from -12 to -3, and then back down again from -3 to -12. So you need to edit program 5C to get your bifurcation diagram, and this includes feedback. Question number 3, you need to look at chapter 6 on fractals. So here is the construction for the Cantor set. So here we have a straight line segment at stage 0 of length 1. At stage 1 we remove the middle third segment, so you get 2 segments of each of length 1/3. At stage 2 we remove middle third segments again, so you get segments of length 1/9, etc. So in class I'll show you how to construct this with pencil and rule. And then you have to apply similar rules. So this is called the motif, and you have to apply a motif and construct the Levy fractal up to stage 7. But again, you have to do this on graph paper with pencil and rule. Question number 4, again we go back to the Henon map. You'll see it's similar to a 2-dimensional map. So the Henon map is in chapter 3. So again, you can see this is a 2-dimensional map. We need to iterate, so you can edit the program. Well, there are a number of programs you can edit here to produce the phase portrait. So you put in an initial condition x0 and y0, and that gives you x1, y1. Then you put in x1, y1, it gives you x2, y2, and you will get discrete points which are plotted on the phase portrait. So you need to plot the first 10,000 points. And I think if you look at program 5A, you'll see that that's a similar program for this one. Next, you need to determine the number of fixed points. And again, this will be similar to, if you go back to chapter 5, we were looking at fixed points for the Ikeda map, and you need to use similar arguments to find the fixed points in this map. So for the Ikeda map, if you look on page 63, you'll see the arguments there. We use the fplot command to plot these curves in order to discover the number of fixed points. Then we need to iterate. So again, you have to write a little program for this and then try and give a physical interpretation of the results. So that concludes the video support for this piece of coursework. Any more questions, you can come and see me in E116B, or if you email me with a quick question, I'll be able to answer. Good luck.